In this tutorial, we'll explain how the particle tracker works in the Rat GUI, and we'll do that by using a simple CCT as an example coil. This simple CCT will bend the particles in a dipole field, so these particles will be bent. And we'll start the tutorial by adding the particle track calculation to the calculation tree as follows. So we right click on the calculation tree, select add calculation, and then from the list choose tracking. Here you'll see that there is the particle tracks calculation added to the tree. And when we unfold it, there are two objects that are connected to the particle tracks. And the first one is the tracking model. This is empty at the moment. It's a model group in this case by default. And the tracking model is basically the volume in which the particle tracks will be calculated, where the magnetic field is calculated, and as a result, what the tracks do in this magnetic field. And there's the emitter. In this case, by default, there is an omni emitter added to the particle tracks. And you'll see the location of the emitter in this circle. It's basically shown here. And because it's an omni emitter, it's basically indicated as sort of a sphere. We'll start by changing the tracking volume. As I said, by default, it's given as a model group, but you can change it by going right click on the particle tracks and then to tracking mesh, add tracking mesh. You can either add a custom mesh or a model group, and we have already a model group here. So a very simple thing to do would be add mesh and then add a cube. This cube would be the volume in which the calculation is performed. And since what I would like to achieve here is I would like to see what a particle beam shooting through the CCT does under the influence of the magnetic field, I will change this cube in such a way that it will be much longer, like so. So now I make it very long, and I make it a bit wider as well to make sure that the tracking volume basically coincides with the whole bore of the CCT. Now, this volume, the tracking volume, is sort of blocking the view. So I can go back to the particle track settings and then click on visibility. And then we'll see that the visibility, if I toggle this, it will toggle the tracking volume on and off. Now, the next thing I'd like to do is change the emitter from an omni emitter to a beam emitter, because in fact I'd like to send a beam through this CCT. And again, I right click particle tracks and I navigate to add emitter, and then I choose beam emitter. And now this beam emitter is added to the list, as well as my omni emitter. I will just remove the omni emitter because for me that's useless. And you see now there is a circle with a line going through it, and that indicates, the circle indicates basically the size of the beam, and the line indicates in which direction the particles are emitted from. Since this would be a very useless beam, to me, I'd like to send the particles through the central axis of the field of the magnet. I will have to change the way this emitter is set up. And I can do that by adding a transformation, and I will choose a rotation because for rotation, we can change the angle. So now it's like this. And if I want to change the rotation vector such that it shoots parallel to the beam axis, basically to the magnetic field, to the coil's axis, I will change the rotation vector such that it rotates around X by 90 degrees. And then we get the result we want. So now the beam will shoot straight through the magnet. An added advantage of the rotation transformation, that's always for rotation transformation, is that you can do a post offset, and I actually want to have my emitter starting outside of my coil. So I move it in Z by minus 50 millimeters. So that now it's sort of already almost outside of the coil, but I can just go a bit further and I move it completely outside of the coil. So what happens now is the calculation assumes that there is a tracking volume. The model is over here. So our emitter, you need to make sure that the emitter is also still in a tracking volume, otherwise you won't see it. And that there is this emitter over here that shoots particles in this direction, so in the direction of the line. It shoots it from both directions, and so half of the particles will end up in my magnet, and it will then calculate what the particles' tracks will be under the influence of the magnetic field produced by this coil. Now, I will add a few turns to the magnet because I think we probably we might want a bit stronger field. So I quickly just change the number of turns in the magnets in the two layers of the CCT. Continue, let's look at some settings of the particle tracks calculation. So first in the main particle tracks calculation setting, so the one of the particle tracks itself, you have the visibility, which we already discussed. It's to turn on and off the model or the box in which you do your particle tracking. Then for the tracking itself, there are some settings that have to do with the algorithm for fitting the particle tracks. So the particle tracks are calculated. There's a particle, and based on the magnetic field, the algorithm calculates where the next position of the particle would be. And the fitting method for this is standard in, well, there's a few in the Rat GUI, they're mentioned here, but the one that is the most stable in Rat is the Rangakata 4-5 fitting algorithm. This makes sure, as it says over here, that there is energy conservation and therefore more stability of the tracks. Then you can choose the tracking type. There's a lot of explanation here about the type of tracking. It would be, in most cases, a good idea to use relativistic particles. And then the maximum step length for the particle tracks from one place to the next you can set, and some tolerances for the tracking. I think in most cases you don't need to touch this. The tracking model, that just has the settings of the box that you're in, so we already went over that. The beam emitter, on the other hand, is maybe more interesting because there you can actually change the type of particle. Standard, there's two particles already in here, like you can set an electron or proton, but if you change the rest mass and the charge, the particle will actually be a different particle depending on what rest mass and charge you choose. Then there is a random number generator that then determines, is used to basically make a random set of particles which have a normal distribution, like a Gaussian distribution for their position, their angle in the horizontal and vertical direction, and the correlation between the position and angle, so the standard deviation of these distributions. You can play with to determine basically the size of the beam and the divergence of the beam and the correlation between the two. So sigma x is the standard deviation in horizontal positions that you can specify. Same goes for y. You can change the standard deviation of the horizontal angles and the vertical angles, and you can set the correlation between the horizontal particle position and angle, which is called emittance, and you can do the same for the vertical position and angle. You can change the number of particles that you want to be tracking and the number of steps during which the particles are live. And that's the most important settings. So let's quickly just do a calculation and see what it results in. The other settings are standard, like the multi-level fast multipole settings, PTK settings, and start calculation time. They are discussed in the manual. They are standard for almost all calculations in Rat. So this is the result of a particle tracking calculation. What you see here is a movie of the particles as they would fly through the box that you have drawn. And based on the particle positions that you have specified. And then the color of these particles, so there is a bit of a shine behind them that basically shows you the overall track. And the color of these tracks is the magnetic flux density at the point in space where the color is. So here in the center, obviously, the particles experience the highest magnetic field, and so there they have about 1.4 Tesla on them when they travel through this point, while more closer to here, it's closer to 0.2 Tesla. You can play a bit with this animation. So for instance, there's this slide bar here. If you go to the animate settings, the particle length here can be changed. Let's see. That this is more, the particle length is more like a visual setting. It's if you want to change this movie and save this as a movie, and the same goes for this time dilation setting. You see here actually this tail sort of shrinks when you change that setting. Let's go back to the beginning, then you see the difference probably better. You see that there is not such a long tail here anymore. Particle limit, this is how many particles you actually want to visualize. So sometimes your graphics card might not be able to deal with so many particles on your screen. And if you run into that, you can change the number of particles that are actually shown with this particle limit. Trail decay, that is how fast this trail here of particle drops. This is all for visualization, so it has nothing to do with the actual physical particles and their physics parameters. This is just to make this thing look visually nice. And you can make them fly back in time by reversing the time, right? So now they go back in time. So this is just to make everything look nice. I think this more or less concludes the tutorial for the particle tracks. If you have any questions, you can always send us an email on info@rat-gui.com. And otherwise, we'll see you in the next tutorial. Bye bye.